In this video, I'm going to introduce to you the topic of chemical equilibrium. You can find this on pages 31 through 42 in your textbook. And one reason we covered the thermodynamics was to understand the basis of chemical equilibrium. Because what we'll find is the variables that we covered in thermodynamics are directly related to our chemical equilibrium. And so the free energy of a system tells us whether a process is spontaneous or not. But it also tells us whether we're at equilibrium or not. And that occurs where delta G is equal to 0. And so we can relate the free energy to what we'll call the equilibrium constant. The equilibrium constant is a value that helps us understand how many products and how many reactants will be present at equilibrium when the reaction is complete. And so all of this is very important for Earth systems because in all Earth processes, they are all trying to achieve equilibrium. Whether they get there or not, whether an outside force or energy or reaction keeps them from getting there, that's a different story. The point is that all processes and systems are heading towards equilibrium. So how we'll begin to describe chemical equilibrium is by writing an equilibrium expression. And so if we have, say, a generic reaction where A plus B goes to C plus D, and where, say, the lowercase letters are coefficients, like 1s, 2s, and 3s, and the uppercase letters are the chemical species, we can write the equilibrium expression. And so the equilibrium expression is always going to be the products divided by the reactants, where the chemical species are in brackets. The brackets are denoting the concentration unit of molarity. And we raise these concentrations to an order of the coefficient. So the coefficients become exponents on these concentrations. And all of that is equal to a constant, the equilibrium constant. And so all chemical equations have equilibrium expression associated with them. Now, the chemical species that you actually put into the expression are either aqueous or gases. Those types of species will have their concentration change at equilibrium. Very small shifts will occur for these sorts of species. And so they are important to follow in terms of where we're at in terms of equilibrium condition. That is different from solids and liquids. If a species is a solid or liquid, their concentrations do not change at equilibrium. They're essentially constant. And we could go in to talk about that more at a later time. But essentially, in these very, very small shifts in concentration or pressure at equilibrium, essentially a very small change in a liquid or solid ends up giving us essentially the same amount or concentration for that solid or liquid. So again, no change, and they essentially are constant at this point. What we find when we do the chemical equilibrium calculations is that no matter what you have initially, how much of the reactant species and how much of the product species you have prior to equilibrium, what we know is that as we reach equilibrium, the ratio of the products over the reactants will always equal K. So you can start on the, say, left side of equilibrium or the right side of equilibrium, meaning product side or reactant side. But in the end, when it's reached equilibrium, it will equal this value of K if you divide the concentrations of the products over the reactants, minding the coefficients. And so let's take a step back and let's make sure that we can all write an equilibrium expression given the rules in the prior slide. So this might be a good time to stop the video. Look at this reaction of calcium carbonate solid reacting with some acid, some H+, making some CO2 gas, calcium ion, and also some liquid water. So write the equilibrium expression. And so what we did was we put the concentrations of all aqueous and gaseous species in the equilibrium expression. And so it's these concentrations that will affect the equilibrium position. So we just covered the equilibrium expression, and we will use that to do equilibrium calculations later. Another way to look at chemical equilibrium is the Le Chatelier's principle. It's a much more qualitative approach, and it allows us to look at a system, see where we're at in terms of the position, and ask ourselves how a disturbance or a change will affect the equilibrium position. And so again, what Le Chatelier said is that if a system is imposed by a change or a disturbance, then the system will shift to a new equilibrium to minimize that disturbance. And so you can imagine that if we have a disturbance, then the ratio of the products over the reactants is going to change because we're no longer at equilibrium. We're no longer at equilibrium. There's been a disturbance. That ratio is off. We either have too many products or too many reactants. So the ratio is not equal to K. But at that point, the reaction will shift towards equilibrium again, such that it'll again equal K. So it will find this new equilibrium position, and it'll do so by minimizing the disturbance. And so let's take our equation that we wrote our equilibrium expression previously, and let's do a few problems using Le Chatelier's principle. So let's do this example where we have our chemical system and we're going to add disturbances to this equilibrium. So this double arrow is showing that we're at equilibrium, and we have our equilibrium expression, which tells us which species affect the equilibrium condition. So with that, which way will this reaction shift? How will it minimize the disturbance if hydrogen ion is decreased? So if we neutralize some of the acid here and take it out of the system, how will the system shift to get back to equilibrium? And so if we remove H+, we're removing some of the reactant here. And so it's going to have to shift to the left, make more H+, make more H+ in order to get that ratio back to equal the equilibrium constant. So it's going to shift to the left if we remove H+. If we increase CO2, so in this system, say we inject more CO2 into the system, how will the system get back to equilibrium? Well, there's too much CO2, so again, that's going to end up shifting the reaction to the left again, because we have too much CO2. In order to get the ratio back to equaling the equilibrium constant, we're going to have to make more reactant, and in doing so, have less product. So we will reach a new equilibrium position, and we do that by shifting the reaction to the left again. What if we add more calcium carbonate to the system? So here's our calcium carbonate, but our calcium carbonate is not a part of our equilibrium expression. Adding a little bit of more calcium carbonate is not going to affect the equilibrium, because essentially at equilibrium the amount of calcium carbonate is not changing. It's actually absorbed into the equilibrium constant. So I think the easiest way to explain this is, because calcium carbonate is not part of the equilibrium expression, changing it has no effect on the equilibrium position. And so before we continue, I just wanted to mention Henry's law. It's an important equation and relationship as we go forward, especially in understanding ocean acidification. And it's a very simple equilibrium type equation where it relates the concentration of a gas in solution, say CO2 in the ocean, with the partial pressure of that gas, say CO2 in the atmosphere, above the liquid. And so the constants are determined experimentally. So these are just numbers that help relate the pressure of CO2 in the atmosphere, let's say, to the concentration of CO2 that we're going to find in some liquid. And so as we can see, as the partial pressure of CO2 increases in the atmosphere, that's going to give us a higher concentration of CO2 in the ocean. So it's an important relationship, and we will use it later on in this class.